In chemistry 11, you talked about saturated and unsaturated solutions, right? Remember that? What's a saturated solution? Nobody remembers. Sorry? That's organic chemistry, saturated bonds versus unsaturated bonds. I'm talking about if I literally just took salt and dumped it into water. What is a saturated solution?
You can't dissolve any more salt.
You can't dissolve any more salt. It just sits on the bottom. Okay? And so any additional salt would just sit on the bottom of the beaker or whatever it was in. Okay? Fall to the bottom. Okay. So what is happening when you put salt into water? We'll just write NaCl. And if I dump it into water, I get and that's basically dissolving, right? Yes. Okay, so we have sodium and chlorine ions in aqueous solution. All right. What is precipitation? Sorry? A solid is formed. So if it was this same reaction, it would be the reverse process. Now, up till this point, you've thought, maybe you haven't, but for the most part, we talk about chemical reactions as going one direction, unless we specifically talk about something going in the reverse direction. What actually happens is both of these are happening at the same time in solution. Okay. So when you put the salt in originally, all right, it's all just dissolving quickly. As you start to form more and more and you get closer to saturation point, the reverse reaction starts to happen as well. Okay? And when they are equal, so when this rate equals this rate, in other words, you can write it this way. Solid is dissolving into aqueous and aqueous is going back in that direction, you get what's called equilibrium. Okay? So the saturated solution occurs when the two opposing forces occur at the same rate. Because initially, this going to the right, the solid going to aqueous wins. And then as you get closer to saturating the solution, this starts to push back and those rates are the same. And that's why you don't see a change. Okay, stuff is actually happening, but you don't see anything happening. Okay, it looks like the salt's just sitting on the bottom. But what's actually happening is the salt on the bottom will dissolve, but then there's ions in solution that will form to precipitate back. And it's just happening at the same rate. Okay, this is what we call equilibrium. A state of balance. Okay. So collision theory, back to collision theory. Molecules of the reactants slam into each other. That's how you form products. That's collision theory, essentially, right? You'd have to do it with enough kinetic energy and the right geometry, but basically you're just colliding to form products. Well, under that idea, the reverse reaction has to happen, right? Because when you look at it in solution, as soon as you form these, if I just gave you this here and said what happens, you're going to say, well, these are going to collide and form sodium chloride. So just by logical reasoning, the reverse reaction should happen, okay? So basically, the product molecules, which in this case, if we're talking about sodium chloride, these are the product molecules, they collide with enough geometry and enough kinetic energy to form the salt again. Okay? And we generally just say the reverse reaction. I'm too lazy to write reaction if I haven't already said that, so I'll just write RXN. And then you get the equilibrium when those rates are the same. I'm repeating this because it's very important. Okay? A state of equilibrium is attained when the forward reaction rate equals the reverse reaction rate. It is not concentrations. It is the reaction rates. Okay? When the rates of the forward and the reverse are the same, then you are at equilibrium. Okay. May I flip the page? All right, so we're going to look at something else. We put sugar into water. The forward process is the dissolving of sugar. The reverse is the precipitation, or you could call it the crystallization, but that doesn't really matter.
Please have in the package as well. There you go.
So if you graph it, if you graph the concentration, all right, and we put in solid sugar, basically, and we let it dissolve in water. All right, and we graph the concentration of dissolved sugar, so the aqueous stuff. Okay. Initially, as soon as you dump the sugar in, you have no dissolve, right? It's just all this, like the instant it happens. Okay. Then, as the reaction proceeds, it's going to be a high rate. Why is it a high rate? Because you have high concentration of this, right? So you have a high rate, and then so the amount of aqueous solution starts to increase really quickly, and then it starts to level off. When it becomes constant, that's your equilibrium point. Okay? So the dissolved sugar concentration will become constant. When that line flattens out, that's when you know that the rate of dissolving is equal to the rate of precipitation. All right. And then you know when that happens, that is equilibrium. So on a graph of concentration, it will level out. It won't be a curve. It'll be a flat line. Okay. Whereas in this part of the graph, the curved part, that's when this dissolving is happening at a faster rate than it's precipitating. All right. So, not every reaction goes to equilibrium. Okay? We will learn later on how to pull a reaction in one direction or the other. Sometimes reactions favor the product, sometimes they favor the reactants. We'll look at that. We'll learn how to maximize yield and all these sort of things based off of equilibrium. Okay? But what do you need for a reaction to be at equilibrium? You need three things. It must be a closed system. So, so you can't have any exchange mass or energy with the surroundings. Closed systems are not easy to make, okay? When I say no, mass is pretty straightforward. So if you're forming a gas, you can't have an open top because the gas is going to escape. That's going to change the mass. Energy, what am I talking about essentially? Heat, like temperature and stuff like that, right? So to insulate something so you don't get an exchange is not an easy thing to do. Sorry? But you'll shift the equilibrium. That's what I'm saying. All right? Well, you'll learn if you're losing energy, it's going to pull it in a certain direction, one way or the other. Okay. Okay. You must have both reactants and products present at equilibrium. So you have to have both. Okay. Why do you have to have both? Yeah, so you can have a reverse reaction or a forward reaction. Reverse / forward to occur. If you don't have any products, you can't have the reverse reaction happening. And if you don't have any reactants, you can't have the forward reaction happening. No. It's not about concentration. It's about the rate. And you'll see probably tomorrow that they're not always equal. Sometimes they can be, but not always. So in other words, if I added sodium chloride to water, and it all dissolves. All right, are we at equilibrium? No, because you don't have any solid NaCl. Okay, if it all dissolves, in other words, it's unsaturated. There's no equilibrium. And then the third thing, I've already said it 3 times, the rate of the two reactions, of the opposing reactions, the forward and the reverse, have to occur at the same rate. Okay, so if the forward is happening at 2 moles per second, the reverse has to be 2 moles per second for it to be at equilibrium. Okay, this one, students forget this one all the time. It's all about the rate of the reaction. It's not about concentrations. Okay, so how can you tell if something's at equilibrium, or what's happening at equilibrium, I guess is a better way to say it. So the macroscopic properties, basically what you can see and measure easily, are constant. So what would be a macroscopic property? What's something you could see or measure easily in a system? Color, that works. What else? Temperature is fairly straightforward. Pressure, you can measure that. The mass of the system. Those are all going to stay constant. They're not going to change. But we don't say equilibriums are static, we say they're dynamic. Okay? So the macroscopic, what you see and what you can measure fairly easily, are not changing. The microscopic ones are. So that is going to be the molecular velocities. And the forces within them. We're not going to talk about those type of things, but if you remember chemistry 11, what are the forces between molecules and stuff like that? Does anybody remember the names of some of them? Intra and Okay, but what else? There's London forces, dipole forces, hydrogen bonding. Remember all those things? We don't really talk too much about that stuff in this class, but those are all still happening. I don't know. Okay. It is the weak force, but in covalent, it is very important because it's the only force, really. All right. So again, in a saturated solution of NaCl, salt is still dissolving, but you don't see it because it's also precipitating at the same rate. Okay. PPT is my shorthand for precipitate. And if I put ING at the end of it, I guess it's precipitating. But I'm lazy, so. All right. That's the intro to equilibrium. Okay. On the next page are questions I would like you to answer. I'll put the key up in the classroom or up here. I'll give you a few minutes to work on those, and then we might start talking about the lab. Or we can maybe do lesson 2. I'm not sure yet. Oh, yeah, we can talk about the test too. Yeah.